Hi everybody, Justin here from chemistrynotes.com, and today we're starting a brand new section. This is section 19, which is kind of like a chapter 19, and section 19 is called the Nucleus and Nuclear Chemistry. So in this video, I'm going to start by kind of introducing the nucleus, talk about some of the properties and kind of some amazing statistics about the nucleus and its density and its size. And then we're also going to start to go over some new vocabulary terms that we're going to use in this section. And finally, at the end of this video, I'm going to introduce like the basic structure of what a nuclear reaction looks like. So without further ado, let's just get started, okay? So at the top of page 1 of our notes here, it says section 19, the nucleus and nuclear chemistry. Now, the nucleus, surprisingly, is not of primary importance to chemists because the chemistry of atoms is generally determined by the number and arrangements of their electrons. And of course, electrons are not in the nucleus, right? The nucleus only contains protons and neutrons. Now, let's not throw the nucleus entirely under the bus here. It does say, but the nucleus and its chemistry has a big impact on our society. I'm thinking mainly of nuclear energy and how we can use nuclear reactions as a good source of providing energy in our society. All right, let's talk about the nucleus. So this will be a review, and then some of the stats I put down should be quite amazing, really, to think about it when you think about the size and the density of the nucleus. But the nucleus contains protons and neutrons, right? Together, those guys make up the mass number, capital A, and we'll get to that. The nucleus is very, very small. The radius, right? The nuclear radius is on the order of 10 to the minus 13 centimeters. So not just microscopic, but submicroscopic, right? If a nucleus were the size of a ping pong ball, right? Those little white ping pong balls when you play paddle tennis, table tennis. If a nucleus were the size of a ping pong ball, the nearest electron, right, which would be the 1s1 electron, that would be almost a third of a mile away. Okay, really makes you recognize just how much of an atom is empty space. All right, top of page 2 of today's notes. We're talking about the density now of a nucleus. Really, the density is essentially indescribable. The density of lead, for example, okay? The density of lead, when I pick up a lead fishing weight, I think, wow, this is really heavy for how small it is. This is really dense, okay? But do you know what the density of lead is, right? The density of lead is 11.3 grams per centimeters cubed. The density of a nucleus is roughly 1.6 times 10 to the 14 grams per centimeter cubed. So that little ping pong ball nucleus, good luck trying to move it, right? The density is indescribable. It's like beyond comprehension. It's like trying to understand Avogadro's number and the amount of sheets of paper it can go up to the sun and all that. It's just, it's beyond our realm of comprehension. Anyway, it says that ping pong ball sized nucleus would weigh 2.5 billion tons. So, nuclei, very, very small, very, very dense. All right. Now I'm going to start to introduce to you some vocabulary terms, but before that I want to mention, we got a double line there, which means I'm moving on. It says the energies involved in nuclear processes, in other words, nuclear reactions, are millions of times larger than typical chemical reactions. Okay, this kind of alludes back to why nuclear chemistry has such a social impact, right? If we could harness the amount of energy these processes produce, we'd be in good shape as far as not being so dependent on oil, for example. All right, some quick definitions. Nucleons. Nucleons is a new term. Nucleons is a particle in the atomic nucleus. So a nucleon is either a proton or a neutron. All right. So your next term I'm going to put on at the top of our next page of notes. And the new term here is atomic number Z. This is not new, actually. Nucleon was new. Atomic number has we give it the symbol Z. Z as in zebra. Atomic number is the total number of protons. Of course, if the atom is neutral, that's also the total number of electrons, right? Mass number, we give that the symbol capital A in nuclear chemistry, and that is equal to the sum of the number of protons and the number of neutrons. So the mass number A is never the amount of protons or electrons or neutrons. It's a sum. The mass number is the sum of protons and neutrons. All right? Isotopes. Isotopes are defined as atoms of the same element having the same number of protons, of course. If they're the same element, they have the same number of protons by definition. But they have different numbers of neutrons. Okay? So one more time from the top. Atoms of the same element having the same number of protons, but different numbers of neutrons. All right, so let's take a look at isotopes here. In the box there, that is my general setup for an isotope, where we have the atom X, mass number A, atomic number Z. So if we're talking about carbon-12 and carbon-14, right? Remember when we talked about hyphen notation for isotopes? I can put those into nuclear symbol notation with my A being 12 at the top for carbon-12 and my A being 14 at the top for carbon-14. All right, next term, nuclide. A nuclide is a term used to describe a particular isotope. So carbon-14 is a nuclide of carbon. Carbon-12 is also a nuclide of carbon. All right, so those are some terms I wanted to either introduce to you, like nuclide and nucleon, or some terms I just wanted to refresh your memory on, things like isotopes, mass number, and atomic number. We've heard some of those before, but I just wanted to put them in our notes here for section 19. All right, next section, double line, big star. It says nuclear stability and radioactive decay. So nuclear stability and radioactive decay. Well, many nuclei are radioactive, which means they can decompose, forming another nucleus and producing one or more other particles. So many nuclei are radioactive, which means they can decompose, forming another nucleus and producing one or more other particles. As an example, carbon-14, it can decompose. Carbon-14 is radioactive. It's used in radioactive carbon dating, right? Or carbon dating. Carbon-14 can decompose or break down into nitrogen-14 plus an electron, okay? That little electron there, by the way, we refer to it as a beta particle. More on that later. But this is a typical radioactive decay equation. So in the box, you see carbon-14 simply breaks down all on its own because it decays. It's radioactive, so it decays from carbon-14 down to nitrogen-14. And then the other particle produced in this particular reaction is an electron or a beta particle. Notice on the left-hand side of the reaction and on the right-hand side of the reaction that the values for Z and A are conserved. All the superscripts have to be add up to the same on the left and right. So on the left-hand side we have 14, on the right-hand side we have 14. All the subscripts, if you will, the Z values have to add up to the same number. On the left-hand side, carbon-14, the atomic number was 6. On the right-hand side, we had 7 and a -1 that brought us down to 6. A and Z are conserved. Now, that boxed reaction on the previous page was one type of a radioactive decay or one type of nuclear reaction. There's a number of different ways to say it. There are many types of radioactive decay, not just like the one in the box on the previous page. So, types of radioactive decay, we have two main categories. First category would be those that do involve a change in the mass number A of the decaying nucleus, and 2, those that do not involve a change in the mass number A of the decaying nucleus. So the one we just saw on the prior page, nitrogen 14 was the result of the decay of carbon 14. So in that particular reaction, number 2 is the category that it would fit into. So we're going to talk about these 2 main categories. We're going to do lots of examples. We'll talk about things like alpha particle production, beta particle production, electron capture, and then we'll talk about a radioactive decay series, and all that's coming up in video number 2. So you want to stick around and check that out right now. See you soon.